So today we are continuing with the discussion of 2018 MCQs from magnetic field and electric field. That's the plan for today. First question is the eighth one. All right. So today we will have to rejoin the link every 40 minutes. People, I hope you all are okay with that, right? Yeah. So this question, a certain transformer has 90 turns in the primary coil and 30 turns in the secondary coil. When 240 volt alternating voltage is applied across the primary coil, the voltage across the secondary coil. This is O level. Even the O level kids can do this. So they ask you for voltage across the secondary coil. So it's Vs over Vp is equal to Ns over Np. That's it. So Vs over Vp will be people 240, and the other two are Ns 30 over 900. That's all. It's very straightforward. Should be very simple. And let's quickly finish this off. 30 and 900 when you simplify, it's 30 once again. 240 and 30 when you simplify, it's 1 and 8 here, right? 8. So I think Vs is going to be equal to 8 volt. So the answer for this question has to be second one. Pretty straightforward, this one. Done. Simple. So a simple question to start with, and then moving on to the next one. What is the next one, people? I don't see any. No. This is electric field in the sense, yeah. This is somewhat electric field, and we didn't discuss this on electricity. It's about capacitors. You can see there are capacitors. It's definitely about electric field because capacitors are involved, but it has an influence of electricity as well. So let's quickly start. A certain in a circuit shown. Sometimes we might have done these questions during our theory class, so you should be able to quickly grab these answers. Okay. In circuit shown, value of each capacitor is 1 microfarad. When the capacitors are fully charged, the total charge stored in the capacitors is the total charge stored in the capacitors. Right. To find out the total charge stored in a capacitor, we need to use the equation Q equals CV. Q equals CV. So let's number the capacitors one by one, or let's just mark the charge. Here we'll say the charge is Q1. Here we'll take the charge as Q2. Here we'll take the charge as Q3. Here we'll take the charge as no, Q3. Only 3 are there. So we need to find out Q1, Q2, Q3 individually, and then we have to calculate it. For that, we need the potential difference across the capacitors. Now we can see there is a 10 volt battery used. So we normally take this one. Here we'll take the potential as 10 volt, and here we can take the potential as 0 volt. Yeah, so at all these places it's 0 volt. Here also 0 volt, and here also 0 volt. Okay, right. So here we have 10 volt, 10 volt, 10 volt, 10 volt, 10 volt, and 10 volt, right? So here you have R and R. So this 10 volt is, no current will be flowing through this. Once these capacitors are fully charged, no current will be flowing through these capacitors, people. So all these 10 volt will be shared among these two resistors. So among these two resistors, there will be equally shared. The potential will be equally shared, 5 volt and 5 volt. And here there are 1, 2, 3, 4, 5 resistors, and across those 5, 10 volt should be shared. So across this R there will be 2 volt. Across this there will be another 2 volt. I think that's enough. Yeah, 2 volt, 2 volt. Across this also 2 volt. And here again 1, 2, 3, 4, 5 resistors. So across this 2 volt, and across this 2 volt, and across only this 2 volt. Across each resistor it's going to be 2 volt, 2 volt, 2 volt, because 10 volt should be distributed among 5 resistors. If they are all equal, the resistance will be equally distributed. So let's mark the potentials at the ends, at either end of the capacitors. Here 10 minus 2, 8 minus another 2, so 10 minus 4, it's 6. So at this point the potential is 6 volt, and at this point the potential is again 6 volt, right? Yeah, 6 volt, and here it's 2 volt. So across Q1 there is no potential drop. I can say that is 0. V1 is equal to 0. and here V2, the potential drop across Q2 is 2 volt, and potential drop across this one, now see 10 minus 2, that is 8 volt here, and here 10 minus 5, 5 volt here. Therefore 8 minus 5, which gives us V3, it's going to be equal to 3 volt, right? And if there is no potential difference across the first capacitor, there will be no charge stored in it. If you take this capacitor, Q2 is equal to capacitance is 1 microfarad, 1 into 10 power minus 6 into voltage across that is 2. So that is 2 into 10 to the power minus 6 coulomb. Hence Q2 will be equal to 2 microcoulomb. And similarly, if we go to Q3, capacitance is 1 into 10 to the power minus 6 into 3. 3 into 10 to the power minus 6 coulomb, which is 3 microcoulomb. And so the total charge will be 5, right? Total charge. Total charge will be 2 plus 3, 5 microcoulomb. Five microcoulomb. Okay, 21st one. Okay, right. 8 minus 5, 3 volt here, and here a total of nothing here, and here 2 volt, and everything is 1 microfarad, 1 microcoulomb. So Q equals CV. Okay, this is 0, right? No change. Because 6 here, another 6 here. Yeah, 6 and 6, 0. So I'm getting third as the answer. Okay. Okay, right. Let's move on to the next part now. Okay, the streaming link. No streaming link. Sorry, today no streaming link. You won't get the streaming link. Guys, did I make a mistake somewhere? Around 6 here. 10 minus 4 is 6 here. Okay. Here also 10, 8, 6 here. Right? Yeah, same current will be flowing. Same current will be flowing. Both 1, 2, 3, 4. Right. So 8 and 5 here. 3. Q equals CV. Okay, right? Nothing here, and yeah, okay. Then we'll move on to the next one. What is the next question? Next one is this one, 23rd one. 23rd one. Sorry. Mm. 23rd, a Gaussian surface S is drawn enclosing a charge distribution of net positive charge as shown in the figure. If the electric flux through the portion of the surface as A is minus phi, which of the following is true regarding the electric flux phi r through the rest of the Gaussian surface? Let's read again. A Gaussian surface S is drawn enclosing a charge distribution of net positive charge as shown in the figure. If the electric flux through the portion of the surface marked as A is minus psi, which of the following is true regarding the electric flux psi r through the rest of the Gaussian surface? Now we have to understand one thing very clearly. Um, so psi is a, now psi is a positive value, but we would minus. So that means through this area we have electric field lines going out, going in, maybe electric field lines going in. So here they have given psi a to be equal to minus psi. So this minus psi is a negative value, remember, it's like something like minus 5. But this is important. Net positive charge, there's a net positive charge. So using that we can decide one thing very clearly: overall flux should be positive. So overall flux must be positive. So what about psi r? So if psi a is less than 0, that means definitely psi r has to be, it has to be a positive value. It has to be a positive value, and its value must be, has to be positive, and its magnitude must be greater than psi. Its magnitude must be greater than psi. So what is the most appropriate answer here, people? I think the most appropriate answer is the fifth one, no, for this question. Fifth one is the most appropriate answer. Fifth one is definitely the most appropriate answer. Okay, because through A we have a negative electric flux, but throughout the entire area we have a positive electric flux to the entire area. That means the rest of the area should give us a positive, what do you call that, this thing. Done. Let's move on to the next one now. Next question is, this is electricity, electronics. No, no, no. What is the next question, people? I didn't see any magnetic field question yet. Not yet, not yet, not yet. No, no. Electricity, electronics. No magnetic field question. Surprising, no? This one is a magnetic field question. 48, 49, and 50. All of them are magnetic field questions. Okay, let's start. An infinitely long thin straight wire held perpendicular to the plane of the paper at point O carries I into the paper. So there is a wire here which is carrying a current into the paper. So here there is a current into the paper. 9 other similar infinite long wires parallel to the above wire are held on the circumference of the circle of radius r with center at O. Each carries current into the paper, same current into the paper. So all of them are carrying a current into the paper. I. All of them are carrying a current into the paper, and that current is I. So yeah, and we know when there are two wires which are parallel and which are carrying current in same direction, between them there will be an attractive force created. Between them there will be an attractive force created, and yeah, so if there is a I here, and here also if there is I, then there will be an attractive force like this, and that attractive force is given by mass per unit length, right? So magnitude of the direction of magnetic force per unit length, force per unit length, that F is given by force per unit length. That's exactly what they have given, and the equation for that is mu naught, this is I1 I2 gildama. So when you have two currents like that, it is mu naught I1 I2 over 2 pi d. That is the equation. Now here there are 9 wires which are carrying a current into the plane, and all 9 of them, 1 2 3 4 5 6 7 8 9, all 9 of them are going to create forces on this. And now there will be a force like this direction, Now let's draw the forces one by one quickly. There will be two forces like this. There will be two forces like this. There will be two forces like this. Okay. And yeah, so you can see all these forces are cancelling out each other. All these six forces are cancelling out each other because they are created exactly in the opposite directions like this. They are created exactly in the opposite directions like this. But there are three more forces which are not balanced out. They are not balanced out, so I'll highlight them in a different color. 1, 2 and 3. These three forces are not balanced out. F, F, F. But the other forces are balanced out. They are cancelled out. The ones in maroon color, they are balanced out. So I'm not going to worry about them. Let's focus only on the ones which are not balanced out, and those ones which are not balanced out are going to create the resultant. Okay, so there will be 3. 1, 2, 3. Okay, they are asking for the resultant. Now this is 30, 30. And wait, all of them are F, F, F. So resultant force, people, what is the resultant force? Resultant force will be upwards resultant, because horizontal ones will be cancelled out, no? F sine theta and F sine 30, sorry, F sine 30 and F sine 30 will get cancelled out, but upwards F plus 2F cos 30 will remain. So it is F plus 2F into root 3 over 2. So when you take F out, it will be 1 plus root 3. 1 plus root 3. Then what is it? For F we have an equation, that is this equation. So this time it's going to be mu naught into I equal current, and the distance between them is what, people? R, no? So 2 pi r into 1 plus root 3. Therefore the final answer is going to be mu naught I squared 2 pi r into 1 plus root 3. That is how you have to approach this question. So the answer for 48th one is going to be, which one is this answer, people? First or second? Direction is upwards. Yeah, direction is upwards. This direction, obviously direction is in this way, upwards. So that upward direction is OY direction. Right, we have 10 more minutes. OY direction. Therefore second one is the answer for 48th. Okay, so you have to remember this and apply that here carefully. Yeah, forces are cancelled out. The forces in maroon color are cancelled out. Forces in pink color, forces which are not cancelled out. Right, done. So with that being said, let's move on to the next part. 49th. Right, this is about, people, electromagnetic induction. Okay, I think I might need some extra time to explain this. Now forget about the Jeep. Forget about the Jeep in this question. It's about the electromotive force induced in the rod here, PQ rod. So let's forget about the Jeep really. A toy car in the figure having an isolated metal axle PQ travels with a constant speed v along a sinusoidal path whose vertical cross section is in zx plane. Okay, zx plane as shown in the figure. At time t equal to 0, the axle PQ coincide with y axis. Okay, time is equal to 0, it coincides with y axis. That means it's somewhere here. I mean, how do I put it? Right, I will draw another separate diagram here and try to mark it. So this is that path. Okay, well, this is the path, and at the when time is equal to 0, the axle is in this way. It's this way, and it is the PQ axle. PQ. This is where it is when time is equal to 0, right? And people, it is moving in this direction. So we need to now focus on electromagnetic induction. So wait a minute, it's moving in this direction. It is the direction of velocity. And how about the magnetic field is perpendicular to this, I think, no? If a uniform magnetic field of flux density B exists throughout the region in the plus y direction and normal to xy plane, the variation of induced EMF at point P of the axle with respect to NQ with time best represented by. Okay, so at when time is equal to 0, let's analyze it. PQ rod. I'm forgetting. Let's forget about the car because we have to focus only on the axle. So let's focus only on that rod. The rod is moving in this direction, and if you look closely, the magnetic field, people, it's in the perpendicular, vertically upward direction. Vertically upward direction. Vertically upward direction. So that is this B. Now here, tell me what is the direction of EMF? What is the direction of EMF? Now B, you have to use Fleming's right hand rule. Remember, so B will be represented by right index finger. Right index finger. B is right index finger. Q, no, not Q. V is right thumb. Right thumb. Correct. So tell me what is the direction of the induced current, people? I think B is right index finger is pointed upwards, V is pointed towards right. So my middle finger is pointed in this direction. For me, this is the direction of EMF. This is the direction of current. If there was a current, it should have been the direction of current. So my battery is in this way, direction. My battery is in this direction. Do you all agree with me? This. So this orange color line is right middle finger. So it should be this way. It should be this way. Okay. So from Q to P only current will flow. From Q to P. In the direction of Y, exactly. In the direction of Y, in the sense it should be from Q to P. Yeah? From Q to P. Now tell me about the potentials. Will you? What can you say about the potentials? There will be a potential at Vp. There will be a potential at Vq. Which potential is greater, Vp or Vq? Vp or Vq? Hurry up. Vp or Vq? Will it be Vp or Vq? Obviously Vp. Yes, Vp will be bigger. Because Vp is connected to the positive terminal, Vq is connected to the negative terminal. Therefore that. So the question is about, read the question carefully. Question is about EMF at end P with of the axle with respect to Q. So that simple E in this question is EMF at P with respect EMF at P with respect to Q. With respect to Q means the equation for E is Vp minus Vq. Vp minus Vq. So the point I'm trying to make here is, people, since Vp is bigger than, but Vp is bigger than Vq. So what can I say about the value of E? So E has to be a positive value. E has to be a positive value. So your graph should be on the positive side. The graph should be on the positive side. Okay. So I think this answer and these two answers should be wrong. And E is not 0. No, E is not 0. E is not 0. So this is also wrong. Here this point, when time is equal to 0, they are saying E is 0. E is not 0. E is not 0 when time is equal to 0. And here it's wrong because E can't be negative. Here also same. E cannot be negative. So here in both these diagrams, E has a positive value, and then people see the Jeep will be somewhere here now. No? Jeep will be somewhere here. So again at this point Jeep will come to the same situation, right, at this point and this point once again. So here here also Jeep will be in the same scenario, here also Jeep will be in the same scenario, and when it falls down again it will still have the same scenario, I mean like this. Here also it will have the same scenario in both these situations. So see, same scenario, and magnetic field is still the same. So every time it reaches the crest and it reaches the trough, E is going to be the same. It's going to be the same. So is that the case here? But where is it going now? The same thing is, that's why the repetition is happening. Now see, the repetition is happening, but where is it maximum? That's the problem now. Where is it going to be maximum? Where is it going to be maximum? Will it be maximum here then? Where is it going to be maximum, people? I'm wondering. Now this is where it's going to be maximum, no, because the reason I'm saying why it is maximum there is, people, because you can see magnetic flux is perpendicular to direction of velocity. Here see, so in these positions induced EMF will be maximum. Here, like here, if you take EMF, the equation for EMF at these points, now at this point, people, equation for EMF here, okay, at this point equation for EMF will be, write a different color, yeah, I'll go with this color. Here induced EMF equation, what is the equation? Induced EMF, induced EMF will be equal to directly BLV, that's all, BLV. Same here also, here and here induced EMF will have the same value, because induced EMF will be BLV, because velocity is perpendicular to magnetic field. But if you come to this point, I think it's going to end. If you come to this point here, this point, right, in between the slope, people, it is moving down while creating an angle with the magnetic field, So here we can't directly substitute B for induced EMF in this case. We have to take the component of B and only induce, substitute. So here if you take the EMF as E dash, here E dash, and if it is E dash is definitely less than E, therefore answer is fifth one for this. Answer is fifth one, because at the crest and the trough and the crest EMF should be maximum.